Thanks for the introduction again, and I will still reintroduce myself once again, just to make sure that maybe someone in the online audience or some folks that have joined will make sure to get my introduction. So my name is Paul Staat, and I am with the Max Planck Institute for Security and Privacy. And in this talk, I present our paper, Anti-Tamper Radio System-Level Tamper Detection for Computing Systems. And this is a joint work with my co-authors, Johannes Tobisch, who is here, by the way, today as well, Zenger, and Christof Paar. And this was within a collaboration with the Bochum-based company PHYSEC. So adversaries with physical access to devices can launch physical attacks. And this allows attackers to extract their information or implant malicious functionality out of or into devices. And for example, an attacker could attempt to read out cryptographic key material or into intellectual property. So the tool case for such attacks includes, for example, side channel analysis, bus probing, or fault injection, to just name a few. And to counter such attacks, system designers can add tamper detection mechanisms to respond to attacks. And this would then trigger some sort of, say, self-destruction, such as the wiping of all of the critical information contained in the devices. So there are already various tamper detection mechanisms which have different protection scopes. And on the chip level, we have seen capacitive coatings on the IC surface or wire meshes on silicon to prevent actual microprobing. On the module level, entire PCBs, such as PCI Express cards, are protected. And for instance, hardware security modules are typically enclosed within an actively monitored security envelope. And this then forms a security boundary around the module. And the third level is the system level. And there are several components which work together. And unfortunately, however, on the system level, tamper detection is an unsolved problem. So there are to date no high security solutions to this. And therefore, in our paper, we introduced the anti-tamper radio, or short the ATR, which uses radio waves to detect physical tampering. So we add antennas to the environment to be monitored, and then we transmit a signal from one antenna to the other. So as the signal propagates, it is reflected within the environment. And thus, when the environment changes, so do the received signals. So by analyzing the received signals, we then can check the environment's physical integrity to make, then trigger like the tamper response. So this wireless approach enables the system level detection even within complex geometries. And thus the approach which we here pursue is very flexible and sometimes can even be retrofitted to existing devices. So moreover, because of the detection mechanism is not based on damaging a security boundary, it further is even reinitializable. So how does one systematically evaluate a tamper detection mechanism? And that's actually a tough question because it's impossible to cover all the attack vectors. And we decided to use needle probing as an exemplary attack vector to evaluate. And we believe because when we can detect a small probing needle, we believe that we are also likely to detect other more invasive tampering as well. So we prepared test enclosures where we drilled small holes into their lids, and in these holes we can insert the probing needles. And further, we added 2 antennas in the environment to measure the radio propagation behavior in the environment. And because we did not want to do all of the tampering by hand, we used a Cartesian robot to position the needles in a repeatable manner for us. So this is what the setup looks like. And this is also the experimental setup which we have used in the paper to gather all the results which we report there. So to measure the radio propagation behavior in the test environment, we use a so-called vector network analyzer. And this measurement instrument gives us the frequency domain transfer function in the gigahertz signal range. So on the right-hand side, we see an excerpt from such a transfer function. And basically what it shows is that how much the transmitted signal is attenuated over frequency due to the environment-dependent signal propagation. So now when we insert the probing needle into the environment or the transfer function will slightly change, and it is this change which we leverage here as a tamper detection mechanism. So to assess the environment state, we use the so-called mean normalized deviation as a metric to quantify the similarity between two measurements, between two of these transfer functions. And it gives us a scalar value between 0 and 1, and the value increases with greater dissimilarity of the measurements. So at the very beginning of our experiments, we used an empty aluminum box as an idealized test environment. And using this box, we addressed our fundamental research question. Can we detect sub-millimeter metallic needles using radio waves? And based on our results, we can answer this question positively. So here, we see that the MND increases as we increase the needle diameter or as we insert the needle deeper into the environment. So the key takeaway from this slide is that we are first able to detect the needle insertion, and second, that the detectability rises with the physical extent of the tampering. So having shown that needle detection in principle is possible, we then went to a real-world case study, which is a fully functional 19-inch server. So here we see the lid of the server, which we prepared for the needle probing by drilling holes into it. And this is what the server looks on the inside. And we can see a number of fans, the CPU and the power supply here. And further, we then added the two antennas for the anti-tamper radio. And these antennas are located in the mainboard chamber of the server. And then we went ahead and measured the ATR response when inserting the probing needle at all the available positions of the server. So this heat map shows the impact of the needle insertion on the ATR measurements. And we can see that the needle causes stronger signal variation close to the antennas. So this result is expected because the server is partitioned in various chambers which are separated by metallic walls. And because of this separation, the signal coverage throughout the server as a precondition for the needle detection is rather limited to the region around the antennas. And thus, based on the server's partitioning, we define a sensitive and an insensitive region. In this experiment, by the way, the server was turned off. And when we turn the server on, this affects the measurement severely. So when we turn the server on, there is airflow, there is vibration, there is significant temperature swings due to CPU load variations. And we can already see here from these MND curve that it perturbs the measurement because there is some dissimilarity indicated. So the question now is, how does this noise affect the detectability of the needle? So to provide an answer to this, we use the following experimental procedure. So we start at the very beginning to take an initial reference measurement. And subsequently, we then compare all of the subsequent measurements to this initial reference. And then at all positions of the sensitive region, we then gather measurements with the needle being outside and with the needle being inside. And each point in the plot shows the median of the MND across the sensitive region, and the color grading indicates the distribution of the MND. So then we vary the CPU load, and repeat the entire process. So in blue, we see the system's behavior when we repeat this entire procedure for a period of 10 days. So this is basically the system's response when it is untampered. So now, when we insert the needle, it is in a tampered state, and this is what the orange lines here show. And unfortunately, when we select the threshold to not produce any false positives, when we select the threshold just above the legitimate state, we were only able to detect around 50% of the sensitive region. And the question now is, how can we restore the detectability of the needle despite these variations? To resolve this, we introduce a setup phase at the initialization of the ATR. So we begin with monitoring the untampered environment during the setup, and we then detect spectral regions with high signal variations. This is during the during the setup phase, where we look at how the ATR response of the radio measurement system behaves when there is no insertion of a needle, just because of the variation of the server. And then, after identification of these regions, we then disregard these identified regions during the deployment of the ATR. So by doing so, we can now see that the two classes of untampered environment and the tampered environment with a needle insertion are actually now very much distinguishable. So this result was obtained with a rather expensive network analyzer, as I've mentioned before. And when we again set the threshold to not yield any false positives, we arrive at detecting 114 out of 117 positions in the sensitive region. That's about 97%. So the question now was, can we also reduce the cost of this measurement system? Because we don't want the measurement system to be more expensive than the actual target that we try to protect. And yes, we can. We actually implemented this system using a set of low-cost single-chip ultra-wideband transceiver chips. And we use these chips to extract the channel impulse response. And using this cheap setup, which is only at 2 times $5, we detect at least 90 out of 170 positions, has 17 positions, which is around 80%. Of course, these results can be further improved, but this is only a preliminary study, and we currently work on improving or investigating further measurement systems, and there's still room for improvement, but of course we can see that the expensive measurement system sets the baseline to show that the detection is possible using radio waves, and that it is actually a viable detection mechanism, even in real-world conditions. Okay, so this slide concludes the talk. We have introduced the anti-tamper radio, short ATR, as a radio wave-based tamper detection mechanism, and this allows system-level tamper detection. We have demonstrated the ATR deployment in a running 19-inch server, and this server had fans, CPU load variation, and temperature swings, and still we were able to demonstrate long-term stable needle detection over a period of at least 10 days. And finally, we have shown that this system can also be implemented using low-cost commodity measurement systems. Thank you very much, and I'm happy to take questions.
We have time for questions. Please give the mic.
Hello. It's a great talk. I was wondering, does the material of like the needle in this case, it's like some form of a metal or alloy. Does the material, what happens when the material changes?
In our paper, we have investigated only different needles, or like needles of different diameter, and only metallic needles.
Okay.
And we are aware that there are some, or we have also discussed some cases in the paper where the attacker could use non-metallic needles. But in the case of probing, say like probing an actual connection on the PCB, a metallic needle would be required, of course, because of the conductivity. And non-conductive materials, for instance, say which are low-loss RF materials on plastic, these would also be transparent to the ATR. This is at least what we believe. We have not yet conducted studies on this, but we are in the progress of preparing further experiments where we will investigate this as well. To conclude, we have not experimented with other materials.
Okay. Just one more. Thanks for that. Like the attack scenario that you are envisioning. Because very specifically needles were used, so I'm wondering, it's like somebody's doing probing on the circuit board. What is the sort of thing you're thinking of?
There are actually actual reports where people have probed bus lines on laptops, for instance, to eavesdrop on the connection to TPM and extract TPM keys from a TPM and then circumvent hard disk encryptions, for instance. So there are various attacks that are based on physical access.
Okay.
But of course, we do not consider a specific threat in here.
Okay.
The needle insertion is just an exemplary attack vector.
Thank you.
So I have a couple questions too. The error rates for the 80%, is that fixed? So the same location can consistently evade detection, or is it there's some variance in terms of the adversary's perspective?
There is some variance. The detectability is affected by a couple of factors. So at first we have the variance of the untempered state. So this is basically all of the noise components. So this is on the one hand, this is the measurement noise of the measurement system, and then there is the noise of the environment, say because of the environmental variation as I've shown here. So these are the noise components which would affect the false positive performance. And then there is the physical effect of the needle insertion on the radio signal propagation. And this is actually fixed. When the environment does not change, the needle detection impact will also not change. It's more the problem with the legitimate environment varying. But there are various ways around this. You could, for instance, also change the frequency range of the measurement, because when you reduce the bandwidth of the measurement, you will also get less information from the environment. But if you increase the bandwidth of your entire system, you will also harvest more information from the environment, which would then potentially boost the detection performance again.
Right, so if you actually change, if the location of the radio, I'm wondering from an adversary's perspective, they can figure out where to insert that is a blind spot vis-a-vis the case, right?
That's actually, that's a really good question, because that needs to be modeled beforehand. And we envision this to complement with a setup phase where vendors, for instance, would verify that the system coverage is given. You could, for instance, we are currently also collaborating with some partners where we simulate the needle detection, in full field wave simulations, and to predict where the needle detection is given. But yeah, that's actually a good question, and the system designer, of course, needs to ensure that the anti-tamper circuitry is located within the sensitive region to be self-protected as well. Yeah.
Is there time?
Yes, there is. Yes, please.
Quick question. So for the low-cost UWB chips, how do you power those?
Excuse me?
For
the ultra-wideband chips?
Yeah.
What was the question exactly?
How do you? I'm just curious about your setup. How do you power them? How do you power them? And I have a subsequent question. If you were to add multiple of them, would that make the detection problem easier rather than having two? If you had four?
That's an excellent remark. This is also something that we briefly discuss in the paper, because when we position more devices in the environment, then we also would gain more detection path. Yeah. So we would have then, when we place multiple antennas in the environment, we would gain multiple connections which we could monitor, even in parallel, to monitor the environment and extend the sensitive region, so to say.
And my first question: how do you power them in the server? You know, are they battery powered? Do you put batteries there, or how does it? Yeah.
Actually, to elaborate on our experimental setup a bit, we relocated the measurement systems on the outside of the test environments. So, so in the setup, they could be battery powered, or you could also power them from the server circuitry as well. But for our experiments, like for simplicity, we used cables to connect them.
Yeah, I mean, you can imagine in the future building motherboards that come with these things built inside of them, so that you get them through the motherboard. Okay, thank you.
Thank you very much.
Oh, that's great. Why don't we thank Paul again for 2 great talks.